Hi everyone. In today's session, we shall discuss about a composite bar or a section, a problem on a composite bar, and how the thermal stresses are acting on a body and one sample problem. So first, what do you mean by a compound bar? A compound section. In the name itself, compound means which is made up of more than one material. Okay. So if a bar or a cross section is made up of more than one material, then it is said to be compound bar, and each material performing different function. For example, if you take our houses and each pillar is based upon a concrete mixture and steel bars like this. So if you take a pillar that is mixed of concrete and in the center you will be having, or in the center of the corners, you will be having steel bars. So like these sections are called as a compound bar. And as the both materials deforms actually, the same value of strain will be defined in the both the materials are said to be same. How let us discuss. So the total strain as the column will be fixed, the strain will be equal in both the materials. So total strain is equal to either strain in steel or strain in concrete. So we know that Young's modulus is nothing but stress by strain. Okay. So strain can be written as sigma by E. So for steel, it will be sigma S by ES, and for concrete, sigma C by EC. Okay. So we know that generally strain is nothing but change in length by original length. So the load will be shared between these two materials. Am I right? So whenever you apply load on the column, it will be equally shared between two materials. So the total applied load is equal to load applied on the concrete and steel. So we know that stress is nothing but load by area. So load can be written as stress into area of the each material. So sigma S into S plus sigma C into AC is equal to P. So now by using these two equations, we can find the strain in each material. Okay. So now let us discuss with one problem so that you will be better understand. So we have taken a concrete column of cross-sectional area 400 into 400 mm, reinforced by 4 longitudinal 50 mm diameter round steel bars placed at each corner of the column, carries a compressive load of 300 kilonewtons. Calculate loads carried by each material and compressive stresses produced in each material. Take Young's modulus of steel as 15 times of Young's modulus of concrete. Also calculate the change in length. Column length is 2 meter long. Take Young's modulus of steel as 200 gigapascals. So from this diagram, from this question, we can draw the diagram like this. So he has given a concrete slab of 400 mm by 400 mm, carries of 4 steel bars, each of 50 mm diameter. So the cross sectional area of the column will be 400 into 400, that is 0.16. I converted into meters, that is 0.4 into 0.4, 0.16 meters. And the cross section of each steel bar or 4 into generally 5 by 4 d square. So, but we have taken 4. So 4 into 5 by 4 into 0.025. Here it is 5 by 4, sorry, or pi d. That's also okay. 5 by 4 d square only it is. So it is 0.0785. And the area of concrete will be this total slab minus this 4. So 0.16 minus 0.00785. The total area of the concrete is this much. We know that strain will be equal in both the materials. So strain in steel is equal to strain in concrete. We know the equation sigma S by S is equal to sigma C by EC, and sigma S is equal to sigma C into ES by EC. And he has given the relation that Young's modulus of steel is equal to 15 times of Young's modulus of concrete. Am I right? So sigma S can be represented as 15 times of sigma C. So it has given that the total applied load is 300 kilonewtons. So the load carried by the steel plus concrete is equal to total 300 kilonewtons. That is 300 into 1000. So WS plus WS. We know that load is equal to stress into area of cross section. So now it comes like this. So with the help of above equations, I could find sigma S is equal to 16.65 and sigma C is equal to 11.1 into 10 power 6 Newton per mm square. So with the help of load equation, W is equal to sigma by A, no? So sigma into S is equal to load by area. So load is equal to stress into area. And the above we got stresses for steel and concrete. If we multiply with these two cross-section areas, we can find out the load of each material. And he has asked us to find out the change in length. Change in length is nothing but strain is equal to change in length by original length. He has given us the original length and we have determined the strain. So we can find the change in length for each material. Hope everyone is clear. So next, thermal stresses or temperature change. Whenever a body is subjected to a temperature, it will be either contracted or expanded. Okay, so then a change in temperature will be given as cross-sectional area into length into change in temperature. So where A is quotient of linear expansion, L is original length, and P is change in temperature. So the change in length A into alpha T, therefore strain is equal to change in quotient of linear expansion into temperature. So stress is equal to E into alpha. So now take an example that a railway is laid so that there is no stress in rail at 10 degrees. If the rail is 30 meter long, calculate the space in rail at 60 degrees if there is no allowance of expansion. Same degrees if there is allowance of 10 mm per rail, and he has given Young's modulus and coefficient of expansion. So rise in temperature is originally it is 10 degrees, right? Raises to 60. So rise in temperature 50 degrees. So stress is equal to coefficient of thermal expansion into temperature into Young's modulus. So you got 120 megapascals. He asked us to find if the allowance is 10 mm. So delta T into alpha T minus 10. So now you got it as 8 mm and change in temperature. And the stress is equal to same. So these are the sample questions which are asked in the exam.